Hello everyone, I welcome you to Kaggle Days Meetup Delhi NCR's Meetup 19. Thank you so much for joining in. We'll be starting shortly now. Let's just wait for others to join. Yeah, so again, welcome everyone. For today's speaker, we have Valerii Babushkin, and he's a Kaggle competitions master, and he works at user data privacy at Facebook. And the topic for today's meetup is recommendation systems in retail. For the agenda of today's meetup, from 8 p.m. to 8:45 p.m. IST, there will be the talk by Valerii, and post that for 15 minutes, we'll be having a live Q&A session. So everyone can drop in their queries, their questions, and they will be taken up by the speaker at the end of the session. Thank you so much, everyone, for joining in. Now, Valerii sir is here. Over to sir.
Thank you very much. Hello, everybody. I would like to thank you all for coming here. I know it's late, it's 8 p.m. As I know, it's 8 p.m. in India, has been told so. And that means that you spend some time to come in late in the weekend to listen to my presentation. And thank you for that. And thank you for inviting me. I'll talk today about the recommendation system in retail, from the uplift trees and bias to the reinforcement learning and counters. So there is a content of the presentation. I will tell you some more information about myself, what I did in the past, so you would know what question is better to state before me, and I'll answer them. Then will be a problem statement. I'll talk about the uplift modeling, the reinforcement learning, and a little bit about the counters. Just a brief introduction of what I did in the past. In the past, I was working in Alibaba Russia, as the vice president of machine learning. Also been learning in X5 Retail Group, which is the largest retailer in Russia, as the senior director of data science and engineering. And I was an attending lecturer and High School of Economy in Russia and the National Bank of Kazakhstan in Kazakhstan. And right now, I lead a team of user data privacy in the Facebook and the WhatsApp. But basically, before most of my jobs, they were connected with the retail, because X5 Retail Group is a retail company. Alibaba is a retail company. Before that, I was working at Yandex Market, which is kind of Amazon of Russia. So all of them are very connected in retail. I also Kaggle competition Grandmaster. I don't compete that much anymore because to be honest, I don't have that much time. And since I reached the top tier as a competition Grandmaster, I don't have that much motivation anymore. But still, Kaggle is a great platform. I'm very grateful for people who told me about the Kaggle, and I'm very happy that I decided to participate there. And if you're not yet participating in the Kaggle competitions, you can fix that today or tomorrow. Do that. By the way, if you have questions, you can state them. I'll see them as a comments, and I'll try to answer them even during the presentation. I think it will make it more interactive and more entertaining, and maybe even better, because the good question is very crucial to have a good presentation. So don't hesitate. If you have questions, don't hesitate to put them. I'll try to answer them. Let's start from the uplift modeling. And before solving the problem, we need to state the problem. Let's do that. Say we have a lot of users who perform specific actions. And each user is in a particular stage and within a specific action and within a specific state. You can ask me a question, what is the action? What do you mean by action and what do you mean by the state? Well, let's say you're in retail business as I was. And what can be the actions the user did? The user can come to the grocery store. The user can buy chicken, beer, bread, butter, milk, whatever. That's all the actions. Or the user can visit the online website of our retail company. The user can also browse some wares or put them in wish list or put them in the checkout, but do no checkout. So these are all different kind of actions. And the actions user does and the stage user is right now is the state. So what could be the state? The user can be in the state that user is just thinking about buy something. Or user can be in the state that this user is already in the shop. Or user can be in the state that user bought something, but it doesn't mean that user is content. User will buy in the future. So these all are obviously different states. And there is also the variety of activities with the retail company. But obviously you can see that this example can be transferred to almost any other business as well. So with the business, we have a variety of activities aimed at transferring a user from one state to another. Say the user in the state of browsing the goods on the website. And if there is a pop-up window with a discount coupon for a milk, that is an action which aims to transfer the user from the just browsing the wares to buying the milk. But that's a kind of action. So probably we might propose a discount, which is a personal promo, or it could be different kind of discount. It could be the category discount, a coupon. It could be different validity periods of offers, etc. Like you just can tell the user that, look, you've got a week. You can redeem a 10% discount for any goods. So you have an activity which aims to transfer a user from state of observation to state of buying. But that's not all. We can consider the very, very simple example, the very simple situation. By the way, I'll check the comment section. Maybe there is some questions. No questions yet, but if you have them, put them. I'll check from time to time the comment section. Consider the situation when there is only one action. We can offer a fixed discount. That means actually that we've got two actions. We can offer discount or we can decide not to offer a discount. So basically we can either give or not this discount, two actions. And to simplify that, let's say that the user also has two actions. The user can either buy or not. Combining these two actions from our side and two actions from the user, we've got four possible outcomes from these combinations. Say we offered a discount and the user made a discounted purchase, but this user would buy without a discount. That means we lost the money, because if something cost $100 and we offered a discount of 10% and the user bought this for 90 but will buy for 100, that means that by offering discount we lost $10. Not a great thing. So the second option is that after offering a discount, the user has bought an item. And without a discount, the user will not buy this item. So that's good, that's great. That's actually what our original goal probably was. Offering discount, and without discount, no purchase. With discount, there is a purchase. Great. They offered the discount, the third outcome, but the user didn't complete the purchase. And anyway, the user will not buy the item with a discount or without a discount. So that means that we spend time and energy for creating a discount, offering a discount, maybe communicating with the user. Sometimes it's not that expensive. Sometimes communication with your users is very expensive. The fourth outcome, we offered a discount, but the user left us forever. That's a rare case, but it still could be. Usually it can be a case if you have any kind of subscription. Let's say you're a company which offers three kind of subscription: the basic level, the advanced level, and the ultimate level. And now you're offering the user who's got a basic level a discount to switch to a advanced or ultimate level. And maybe this user just forgot that he's got a subscription, and then you remind him you got a subscription, and he think, okay, I've got a subscription and I don't use it, I need to cancel it. Basically, you try to transfer a user from one state to another, but the outcome is very, very different to that. That's a rare occasion, but it still can be an occasion. And there is a great picture which illustrates this. It is taken from the algorithmic marketing, artificial intelligence for marketing operations. And later, if you will see any equations, if you will see any citations, I will put the name of the article or the book they're taken. So if you're interested, you can read more. And this book is a great one. It's useful enough and it's simple enough, which is a rare occasion in terms of machine learning and in terms of artificial intelligence. So what we can see on this plot, we can see that, say, the black line is what we will have with no actions. And the red line shows us what we will have with some actions. And basically, before this period of time, the black and red line, they just the same line. So that means that giving a discount here is actually a loss. And here, by giving a discount, we can see how much money, how much more money we will have if we will make a specific action. We can also illustrate this having this quadrant, like this green corner. There's a positive lift. These are the people who wouldn't buy without a discount, but they bought with that, and that's a positive lift. Do not disturb is the people who would buy without a discount, and by offering them a discount, you don't have a positive lift, you've got a negative lift. Sure things and lost causes means that basically you will not affect your users, but still you are spending some time and maybe money to communicate with them, so you don't need that. What we need is to find out these people in the green corner, and that would be great. And there is a way how to do that. It is called an uplift modeling, but before switching to that, I'll check the comments section. Give me a second and I'll do that. Okay. There is no questions to me yet. Okay, so let's move further. We can build a decision tree, maximizing the difference in uplift between control and target groups. So how it's done? What that means? Let's say you've got your user base, and then you offered to some of them a discount, and some of people from a user base, they receive no discount. So that means you already have two groups. You have a control group, the group which received no discount, and a target group, the group which received a discount. And then what you need to do to build a decision tree, maximize the difference in uplift between control and target groups. And this can be calculated in three ways. That's pretty straightforward, which is KL divergence, or I'll try to pronounce the surname of this guy is Kalbeck-Leibler. Euclidean distance, another guy, this time is a Greek guy, and chi-square distance. Well, basically, if you remember some stats, it's all the measure of divergence, or the gap, or the margin, or difference between two distributions, PK and QK. And here's the way how to calculate the P and Q, where YI is does this user receive. No, YI means Does this user made a purchase or not? So if purchase is made, it's 0. If not, if purchase is made, it's 1. If not, it's 0. And WI means, did we target this person? Like, if so, say if we offered a discount, it is a 1. And if the person who's been offered a discount bought an item, it's again 1. So 1 times 1 is 1. We calculate how many times we've got ones for people who received a discount. So, and contrary to that, we will do another action. So then this is a 1, this is a 1, then W is 0, and W is 0, then this person received no purchase. So here's a number of ones, and here it is equal to 1, then the person has bought the item, but again received no discount. So basically it's two different distribution. Bought item and received a discount, bought item and didn't receive a discount. And we want to make these two distributions as far away from each other. If you want to read more about that, take a look in the causal inference and uplift modeling, a review of the literature, which is from the GMLR workshop and conference proceedings. Here's the reference. I will use this picture to illustrate that. Maybe it will be easier to understand. So let's say we've got 30,000 users. And for the 15,000, we offered a discount, and for 15,000, we did nothing. And it turned out that, for example, let's say our action would be how many people didn't buy, So 10% didn't buy here, and 8% didn't buy here. So basically, it's better because that means that 92 bought, and here means that just 90 bought. So if you take a look at how much of them didn't buy, that means that an absolute uplift is 2%. Or if you take the relative, it's 25. So 8 to 10 is 25% difference. But what we want to understand is there is some subsample of people who it is better to offer a discount, and if there is a subsample of people to whom it's better not to offer a discount. And we're building the tree based on this criterion. I by myself prefer the KL. That's very easy, and it's just very easy transfer to many other machine learning stuff like entropy and even the log loss. So there is intrinsic linkage between these, and that is good. Let's say we're building the trees. So we have an input features for each user. We have somehow described each user with a feature vector. And now we just have this criterion again, answering the simple question. Is the specific feature has a specific threshold? And then we split the original 30,000 into two groups. And you already can see that the first group has an uplift of just 1.3%, but another one has an uplift of 4.2%. So we're already being able to separate our users into two groups. And this group is much more lucrative and much more efficient in terms of offering a discount. But we can proceed further, do it again and again and again and again. And at the end, we just split our original 30,000 users into 5 groups, 1, 2, 3, 4, 5. This is the terminal nodes. These are the leaves of the trees. And you can see that here it's 6%, 3 times higher than the original one. Here it's 4.5, still not bad. Here's 3.1, here's 1.1, and here's 0.2. So basically, then you can understand, okay, I have an uplift. That means the probability that the user will buy some stuff. I know how much the discount costs to me. Now I can understand, okay, if I spend for a discount like 1.5%, that means that these two makes no sense because I'll spend more than I'll gain. But these 3 are very good. Or if I have a limited offer, that means that it's better to start from these people. And this picture, this image, is from Uplift Models for Predictive Modeling in Finance and Insurance. And Leo Gelman is one of the original authors of Uplift Modeling. There are many ways how you can produce the Uplift Modeling. The Uplift trees is the best one. The others are, say, more inferior. And if you're interested why, again, take a look here. Before going further, I will again check the comment section. Okay, no questions. Let's proceed further. So, if we build one tree, we can build a whole forest. The same idea as a random forest or any other. It will reduce the variance. We can simulate each impact separately. So what does it mean, simulate each impact? Until now, we just reviewed a very simple, very baseline example. We've got one action, we've got one output. But of course, we can have more than one action, and we can have more than one output. So it's not a big deal to train the decision tree for more than 2 possible outcomes, because you can train the decision trees for binary classification, multi-classification, regression task. It's not very hard to do. So what can you do if you have number of actions? One of the way you can do is you can train different trees or different forests for different actions. Then you'll get a predict for a specific user from each model. And basically what you can receive from this is not even the single output from each model, but the distribution. Because you are doing this here with a distribution, that means that you don't have to receive just a point estimate. You can receive the point estimate with a confidence interval, or you could receive the distribution parameters. And the final choice can be made through the Thompson sampling or epsilon gradient. So, and if you know what Thompson sampling is, you already understand that we are very, very close to reinforcement learning. And by the way, here I just gave you a recipe for next best action recommendation system. It's ready. That's all you need. Before I will proceed further, I'll pour a cup of tea, because it's kind of hard to talk without a pause for more than 10 minutes without drinking some liquid. And again, I will check a comment section. Can you give an intuitive explanation of KL divergence? I'll try. It's not usually easy to make an intuitive explanation, but I'll try. So let's say there is PK and QK. And obviously, if PK is equal to QK, their ratio is equal to 1. So if PK, say, is 0.5 and QK is 0.5, then 0.5 divided by 0.5 equal to 1. And then the logarithm of 1 is 0. And that's it. So that means that there is no divergence. That means that these two distributions are equal. They are the same. But if PK is, say, 1 and QK is 0.5, then there will be a 2. So the logarithm of 2, well, if it's natural logarithm, it's close to 1. If PK is 2 and QK is 0.2, it is 10. So the logarithm of 10 is even bigger. And then you see it's bigger and bigger and bigger number by then we've got. Vice versa is also the case, because the logarithm of something less than 0, but greater than, less than 1, but greater than 0, is the negative number, but it can be infinitely large. And again, it shows you a divergence, the gap between two distributions. That's an intuitive definition. description. No, it's not an intuitive definition, it's intuitive description. As you can see, it's very close to Euclidean distance, which is basically the square difference between pk and qk, and pk and qk can be calculated in this way. It just could be a point estimate of two distributions. If it's not clear, tell me now. I'll try to describe in other words. If it's okay, so what's the P and Q signify? Well, the P and Q in original case stand just for two different distributions we compare. But here P and Q stays for two things. Let's review the P again. So what is the P? The P is equal to 1 in a numerator. Then, it's equal to 1. Then the target variable value, then the user has bought an item and the user has received a discount. So if the user received a discount but didn't buy, it's 0 times 1, 0. If user has bought but didn't receive a discount, it's again 1 times 0, it's 0. So it will be just 1 only in the case then there is both a discount and a purchase. And basically it's a ratio. We take all the users who received a discount and check how many of them made a purchase. Here we do opposite to that. We take all the users who didn't receive the discount and check the ratio, how many of them bought. So basically we want to have these two things as far from each other as possible, because if they close to each other, if the ratio of users who bought and received a discount is the same as the users who didn't receive a discount but also bought, that means that there is no uplift, no gain from our discount. And we want to just find out, want to separate, want to exclude these users who will buy only if they will receive a discount. So that's the meaning of P and Q in this case. Any other question? I'll switch to reinforcement learning part. I'll wait just 10 seconds. And if you're silent, I'll move further. Meanwhile, I'll drink a tea from the wooden cup. So PK greater than QK will not nullify the effect of QK greater than PK. Well, basically, it's a good question. So let's take a look again here. I'm not sure you see, by the way, do you see my mouse? Because I'm trying to highlight something with the mouse. I'm not sure you can see it. I don't know. Okay, let's assume you see my mouse. Anyway, so let me point out again the question to make the answer better. PQ greater will nullify the effect of QK. Well, that's a point. That's actually a good point. That's why we need to split them. We need to find out which users, by receiving a discount, would behave in a way that will decrease the chance that they will buy. So that's why we need to separate these users. Well, here we didn't see this extreme case here, like an uplift still was positive, but there could be the negative uplift. And the main idea to find out these people and separate them. So you need to give a discount to these people, maybe this, but probably not to these. So that's the main idea. Yeah, the divergence could be other way. But we are trying to increase this one. And so this one will be positive. Then PK is greater than QK. Because if it's smaller than QK, it will end up in something less than 1. And the logarithm of thing less than 1, but greater than 0, is a negative value. and we are trying to maximize this difference. So that's why we are aiming in maximize. But say if we can find a split which will improve the left node so much that even the negative uplift in the right node will not harm it, we will do that. That's a great question. That's a great question. I'll move to another part with the reinforcement learning. Brace yourself. So the next best action recommendation system can be described as a reinforcement learning system. If you have had some experience with reinforcement learning, you know that one of the basic algorithms there is a thing called SARSA. Basically, almost every reinforcement learning still follow this approach. That means that you have state, action, reward, state, action. So you're in some state, everything can be described in some state. Then you have a number of actions you can perform. Then after being in this state and performing this action, you receive some reward, which can be positive or negative. Then again, after receiving a reward, you are in some state and you can perform some action. State, action, reward, state, action, reward. And if we build Uplift modeling system, that means we already have an input state which describes our customer, our user. And we have one of many available actions, which kind of discount to give for what amount of discount, etc. That's an action. And we have an actual reward. This is a cost of campaign and return on investment, or average purchase price, etc., etc., etc. What you can do in the input state, you can also incorporate, you can inject the output from your Uplift modeling, and by this, in your neural network, you will incorporate the knowledge gained through the tree-based algorithm, which usually is a good choice. And we can get along with just two equations. So basically here, it's how it looks. I just wrote down here a very, very simple temporal difference equation, which calculates the Q value and Q learning. And I've got a sample of the code. I can share that afterwards. It's in my GitHub. We're going to give you an example based on the toy project with a self-driving car, how this can be incorporated. But basically, if you are aware what is root mean square error is, this is very, very much the same. We will not dive into technical details of making this work in the code, but it's very, very feasible. And that's great. The problem here is that what we do, we're just trying to look one step ahead. Sometimes that's enough, sometimes not. And that's why we can try and look into the future a little deeper. If you're interested in a more wider exploration on this topic, take a peek in a long peek into reinforcement learning by Lilian Wang. It's a great article. But still, we can try to use Monte Carlo estimation. So if you got step one, just looking one step ahead of the future, is a temporal difference of step 1, 2, and then you can make infinity large, which is Markov chain, Monte Carlo estimation. The three ways described here. If you perfectly know the state of your system, if your system is not a stochastic and determined, you can use a dynamic programming, which is not the case almost everywhere. The temporal difference tries to look one step ahead. The Monte Carlo tries to look many steps ahead, and then you could try to find the best one. And the wider description is in the David Silva Reinforcement Learning course, Lecture 4, Model-Free Prediction. What are the benefits of this complex, it could be looking like a complex system? It is relatively easy to integrate into existing system, especially if you don't look far ahead, because all you need is just this to equation, and it's very, very easy to inject them. It is important to identify reward correctly and solve the lag problem. What I mean by that? Well, because in the real system, then you have some campaign and you've got a reinforcement learning algorithm, and you just produce an action, you will receive a reward and result of your action in a long time, a day, a week, maybe a month. So that's a lag problem. You don't have all your outputs or results of your outputs immediately. You also need a large data set. So basically, reinforcement learning is not for the people who just have a 10,000 samples. How many you need? That's a fair question. We had a decent results on the next 5 data. The next 5 data, we've got like 20 million purchases per day. We've got 18,000 shops around the country, so enough of data. What is the benefit? The benefit is that the system is adaptively tuned. You can leave it, and if you have a shift in behavior or something happened, the crisis or something like that, it doesn't matter, because the system will just understand that, okay, the reward changed, the behavior changed, and the system changed itself. What is also very appealing is that reward can be changed if it's necessary. One day you could strive to increase your revenue. Another day it could be your margin or net profit. The third day it could be just the traffic, whatever. You still can do that. And the bonus content about the contest part, I will check the comment session. So no questions. I will switch back to the counters. So counters. Counters allow you to take into account user interaction with different elements by hour, day, week, month, with exponential decay. And you can have a separate counter for each event type. The counter has 2 main characteristics. It's event weight, so it can be the price of the product or the event fact, and a coefficient for exponential decay. What does it mean? Say you can have a counter how much money this user spent in the last hour, day, week, month. But of course, if this user spent a lot of money just a month ago, it's not the same if the user spent a lot of money just an hour ago, and that's why you have an exponential decay. That's the information far away in the past. It's not that important as the information right now. That's a pretty common concept in time series prediction and machine learning. And well, it's even the same in reinforcement learning, because if you take a look into this gamma, which is a discount, which is again exponential. Every time it just iterates through itself. So 2 steps ahead is gamma, which is less than 1 in the power of 2, and 3 steps ahead power of 3, so that's exponential decay as well. But counter helps you to have a good representation of your user's behavior in a kind of cheap way. Let's say the counter is a good approximation of the embeddings, where you have another counters, you can represent your user behavior, but the drawback is it's still a manual way of manufacturing the features. But it's an easy one, and it's very widely used. And you can read more about model impression discounting in the large-scale recommended systems by KDD 2014. That's it. I know that it's been planned for 45 minutes. I did it in 40 minutes. Hope you will forgive me for that. If you would like to ask some questions, you can do it either now, or you can find me on the LinkedIn or even the Facebook, and try there, and I usually trying to answer pretty fast. Thank you very much for attending, and if you have a question or questions, I'm ready to help you.
Yes, I don't see a lot of questions now. Let's just wait for a minute or two and then we'll wrap up.
Perfect. let's say the minute. And well, anyway, you can find me following the link. I know that sometime you need a time to digest, and then you will pop up with the questions. Yeah, okay, go on. Out of the topic questions, my favorite ones. I'm ready. Which Kaggle challenge are you involved in? At this moment, no Kaggle challenge I'm involved in. Before, I mostly competed in the computer vision ones, but basically I participate, as you can see, I won 6 gold, 20 silver, and 4 bronze medals. So 30 competitions with the medals and 47 overall. I also love to participate in Santa challenges, which is discrete optimization, but it's mostly, as you can see here, open images, IEEE signal processing, and pneumothorax. All of them are computer vision, but I also was quite successful in NLP, in time series analysis, and in basic tabular data computations. How did you get into data science? What's your Kaggle journey? Well, good question. In 2013, I started to work in the Danish company called Force, and this company was producing and still is producing the equipment for a full analysis. And it's got two branches. The first branch is chemistry methods, a lot of acids, alkaline, etc. And the second one is near infrared spectroscopy. And in near infrared spectroscopy, what you've got a light going through some sample, and you know what your light was before this sample and after your sample, and you know how intense your there's the sun, you see that how intense your light was on a different wavelength, and that's the kind of features you've got. And for that you need to create a prediction model which will be very fast and very reliable. So it has to predict how much protein this sample contains with the tolerance no more than, say, 0.03%. Very, very precise. And I've been doing that for 2 years. And then a friend of mine told me, well, there is a Coursera data science curriculum or something like data science track. Machine learning is a hot topic. And that was scary. But then I had a look in this. I found out that I basically have been doing the machine learning and data science for the last 2 years. We just called it chemometrics. And I went through the number of boot camps, let's say that, which were just very intense 5 or 7 days training, like intense starting at 10 and ending at 8. And then I moved to the bank. I worked in the bank for the 3 months, and someone told me there about the Kaggle, and I joined, and that was 2016. So you see the time's going. And that was an all-state competition, was my first competition, and I spent so much effort, and I won the silver medal, but I made a grave mistake. I also sent some submits from my wife accounts, and basically we've been banned for sending almost the same submissions from the different accounts. And that was very disappointing because I spent so much effort. There were more than 3,000 competitors in this all state, and I ended at the place like 91 or 81, so quite high. And then I was just very, very disappointed for that. But 6 or 7 months later, I gained some willpower to start compete again. I won silver medal, then gold medal in computer vision competition. And the interesting thing that I became a Kaggle master in 2018, and the same day I had an on-site with a Google in Zurich, which obviously, so I hadn't slept well. I just won this medal, then I had an onset, it went good, but I still decided not to go to the Google that time. So then I started to compete like mad because I had a goal to become a competition grandmaster. And I became one. And then I became grandmaster. I competed a little bit more. My highest position was 23rd. And then I thought, okay, do you really want to spend so much time to try to achieve top 10, top 5, or top 1? Because that's a lot of time you need to spend. I decided, no, that's good enough. That's good enough. So that's my journey. Do these methods deal with cold start problems? It's a great question. Well, in uplift modeling, you kind of already deal with the cold start problem because you need to have then initial sample of people to whom you send a discount, which is your start. You don't have the cold start problem in uplift modeling. You can't start without some initial data. So yeah. You could try to do some kind of categorical analysis on your users and to exclude the people who probably really don't need the discount, but still no way to deal with. Okay, another one. Could you please add your thoughts on ILS for recommendation? How to approach recommendation problem regarding a new use case? What I think that ILS is a good one. So it's basically very close to the metrics factorization, which is basically the case. But what you can do with a new use case? Let's say you have two different use cases. You have a use case and you have a new user. It's a new use case. Well, it's a lot of sun, right? It's very sunny in London. And you've got a new item. What you need to do, you need to have a really good description of your users or your items. And even if it's new user or new item, but the description is good, your model will catch some similarities in this description between the new and existing ones. So that means you need to have very good embeddings. One of the most simplest approach in this is not even to have embeddings, but I have a thing called well, it's not collaborative filtering, it's content-based filtering. So like you have a content, if it's an item with the same content, it's a similar, let's recommend it to the user who you would recommend this content and the similar ones. But another approach is being able to create embeddings, and here's a good question. What and for you need to create embeddings? You can create an embeddings out of the item description, item images, etc., etc. So all what we do in machine learning is trying to find the best representation and just use it in the model. So so far, what's working at Facebook been like? The Facebook is a great company. It's one of the, I would say, two best companies in the world. The first one is Facebook, the second one is Google, but that's just my opinion. It's just my opinion. And a lot of great and smart people. The only drawback that here in London, and I think in any other country, we have to work from home, and that's a drawback. It's not Facebook fault, basically, but it's interesting. And I missed an office with the free food, basically. And by the way, the office is this building is a new Facebook office in the King's Cross, and that will be the main office. So they will finish this building in 3 months, and in autumn it will be my office. There are another 3 buildings for Facebook just on the right of me. You can't see them, but so the Facebook is pretty far pretty close to me. How to integrate privacy preserving machine learning into the RegSys? Good question. So There is an approach in machine learning community which is called differential machine learning, which tries to prevent the reverse engineering for embeddings. Like maybe you've heard these models like GPT-3 or huge transformers, they actually they're not human-like. They don't think, they just learn. And that means that if you sample quite a lot from them, with some preservance, you will receive the information they've been trained on, and if they were trained on some privacy specific information, you will get this. Like researchers showed like they've been able to extract their phone numbers, emails, the private information, etc., etc. And there is a way how not to achieve that. So one of the things in the privacies is to implement this differential privacy into your machine learning train routine. What are resources to learn how to implement this as a developer? Well, the best one is just to open the Google. I'll do this like differential machine learning. Probably it's called the differential privacy machine learning. Yeah, the differential privacy machine learning. And there is survey and review and how to do that. And there are many different approaches, so it's better to read them, but you know what words to use in the Google. And that's the good question is half of the answer. But that's not an easy topic. Oh, the flurry of the questions, isn't it?
Yes, yes. I believe we are done with the questions now. So it's time that we wrap up. Thank you so much for coming over, sir. It was lovely having you over. The session was really enlightening. I believe it was helpful for everyone. We do have another question now.
Well, I'll be very glad if I can work with you in any upcoming Kaggle competition, how to achieve that. Well, to do that, I need to compete in the Kaggle competition, and I don't see that I'll do that in the future because I don't see an interest in competitions. They're very much the same for me. I already have done all of this. So maybe if something is reinforcement learning will come and will be something interesting, I'll try to participate, but until now, or maybe if there is some with the time series prediction like it was for a 2 Sigma a year or two ago, that was really fun. I like the competition there. You need to write a code and deploy it and just wait for your results, which the estimates in real way along the time. But so check around. You know my LinkedIn. You can write me periodically, like you can write me, man, there is an interesting competition. Do you want to participate there with me? And I'll tell you, like, most probably I'll tell you, no, I don't want to participate. But if it's really interesting for me, because, well, different people found different things interesting, I will participate.
So again, thank you everyone for joining in, and thank you so much, sir, again.
Thank you for inviting me, and I wish you a great evening. And I will use this opportunity with the sunny weather in London and we'll have a walk. Thank you very much.
Yes, thank you.